Hello everyone. The next section of this course will be a subject called differential equations, which is sort of the next step and another version of the calculus that you have already learned. But I want to try and justify this to you first. So let's take this example. We have a linear spring. We have a mass, which I will connect. And so if I was to hold this and just leave it, it will sit still with the spring extended a certain amount. But if I give it an initial impetus and keep my hand still, this mass will go up and down. And you already know this. This is not a surprise. I can add another, I won't do it directly, but let's suppose this beaker had some water in it or some other liquid. So if I did this, okay, and it was going in and out of the water or in the water, what you would expect is, like you see it now, the motion is slowed. Now, in this case, it must have slowed because of the spring situation, but nevertheless, the fluid, of course, would create drag. Okay? Now, this demonstration is pretty simple, and it's something that an elementary student who has never heard of calculus would still be able to predict the answers. Okay? So now what I'd like to do is to move past the demonstration and look at it on the board. Now I've just zoomed in a little bit here for just this demonstration. So here is the spring. It's being held from a bar or something like that. And here's the mass, and it's inside this beaker. And on the board, at least, we can add a fluid. And we get this to and fro or oscillatory motion. So let's look at it from a grade 11 standpoint. What forces are present, physical forces are present right now in the system. So we have the force of gravity, which pulls the mass down, spring everything down. We have the spring force, which is going to be pulling in the direction opposite to, well, depending on how the spring works, but it's pretty much pulling it upward, I guess, at all times. In this particular case, because it doesn't go past the equilibrium point. And we're going to have hydrostatic drag in the fluid, and that would, you could argue also in this drag would be a certain amount of friction in the spring, but we're going to leave that for now. Okay, now if we think about what we learned last year in grade 11, you say that Newton's second law says that the net force is equal to the sum of all the forces present. Okay, fair enough. And this is also equal to ma. Now, reminding ourselves, we have a mass, that's okay. What acceleration are we talking about? The observed acceleration, okay? It's not a magical one. It's the acceleration that actually occurs due to the summation of all these forces. So what we would have then is F net is equal to the spring force plus the drag force, the hydrostatic drag force. We're going to leave gravity out because gravity is the same everywhere on the spring and doesn't affect materially the motion here. Now, we learned that F net is equal to ma. We learned that the spring force is equal to negative kx. And we learned, and we don't know this, but you will be told, that the drag force, at least in reasonable approximations at low speed, is some constant, typically b, times the speed. Okay? And there's no squares, everything's pretty linear here. So let's rewrite this a little bit based on a bit of calculus knowledge. And I'm taking my time because I just want to set up this for you before we get into the nuts and bolts of the theory. The acceleration is equal to the velocity derivative or the second derivative of the position. In calculus, when it's a time derivative, we can use two dots over the x instead of a prime. Okay, and then we have velocity is equal to dx dt, and this is going to be equal to x dot. And so now our equation looks like this. We have mx double dot is equal to negative kx plus b x dot. Now we don't know if the constants are positive or negative, so it really doesn't matter. So we could write it this way. We could say mx double dot plus kx plus, sorry, let's do it in order of derivatives. So we'll say bx dot plus kx equals 0. So what we have now is an equation that has the position, but also the first and second derivatives of that position within the equation, and it's equal to 0. And so the question now is, when we solve this, what would our solution look like? I don't mean the specific equation, but what are we actually trying to do? And so our solution will be x of t in this case, some expression, and the specifics of that expression is what this section of the course is about, so we'll just leave that for now, is that has constants and functions of t but no derivatives So we are looking for some function x of t in terms of t and whatever else that you could plunk in here and this would be equal. That's what a solution of a differential equation looks like. And we're going to get back to the technical details. But just another aside to this before we get into the more specifics. I'll leave it zoomed in just now. Technically, a differential equation is any equation which contains differentials. So you might have something like this. dy is equal to 2x dx. Or better still, dy dx equals 2x. Okay? Now, this would be an elementary derivative that you might have seen. And we might also have, as I wrote a second ago, dy is equal to 2x dx, so we do it implicitly. And if we wanted to compute y, we would integrate. So we'd have integral of dy is integral of the 2x dx. And so one of the cool things, as I said in the last lecture, is we're integrating here, but we're integrating with respect to y on this side and with respect to x on this side, and yet the equality is preserved. Normally in algebra, if you say, okay, you have to multiply, but you're going to multiply by the same number or you're in trouble. Now, the main thing here is to appreciate that this solution, so when we're finished here, we get y is equal to x squared plus a constant. And so you can see that y of x is expressed completely in terms of x and some real number. Whereas here, we had differentials, and x was not explicitly described. And then so this, in effect, is a solution to this otherwise differential equation. But it's never normally described that way when you study it, because this is perceived to just be integration, elementary integration. And so we don't normally talk about differential equations until we encounter cases where the derivative is in the same equation as the function, where we need the specialized techniques of solving differential equations. But in effect, you've already been doing them when you solve your calculus, because the simplest way to solve a differential equation is simply just to integrate. And which is in my example, trivial example here. But we need to get into it in a way. Now, of course, there's textbooks written on this, and you'll take a whole course in it. I'm not going to prove things, and we're going to cover the parts of differential equations that are relevant to what I want to do with you in the AP Physics course. Okay? So we will stop this lesson and pick it up again with a more formal approach. So first off, we're going to spend a few minutes here talking about all the different ways that we classify differential equations. These equations were first known probably at the end of the 1600s. As you can see, just even from the weight-mass system, they arrive out of nature and fairly quickly. However, they're mainly, it got into theory probably more into the 17 and 1800s. Certainly people like Riemann and Euler, as well as Gauss and a host of other mathematicians contributed enormously to this background. So this is old calculus. It's been around a long time, and there's a lot of established concepts to it. I should add also, although we won't do it in this course, is that there's a substantial amount of instruction related to solving these equations using a computer. Because in the real world problems, you're going to have equations that are going to be very difficult to solve analytically, or you may have too many equations. We're dealing with a single differential equation here, but you could well have many of them together, and then solving something like that becomes quite a complexity. And this is, of course, where we benefit tremendously from the ability of computers to solve problems. All right, well, let's get started here first. The first type of, there's two basic classifications. So we have differential equations, and so let's just call it classification. And the big describe what you call, say, the type of it is going to be based on the, so this is based on the derivatives. So we have partial derivatives, then it is a partial dE, okay? And these we will not spend much time with. These are quite difficult and require a fair amount of underpinning knowledge to them to solve. So we'll touch maybe a little bit of it later on in the course at the end, but you really won't be solving these ones. However, then there is the ordinary kind, and these have ordinary derivatives. So here we have, say, f x, okay, and here we have what we call ODEs, and they have ordinary derivatives. to see, dy dx kind of thing or something like that. And this is the type we're going to spend time with. There's another nature classification as well. So we have linear, and so this is where the terms of the DE are combined in a linear fashion. So as I showed you a minute ago, my original remarks, but you could have even something like x dot, so say kx dot plus wx equals 0, okay? So the point here is that this term, these are added or subtracted, whatever, and they are not combined. So this is a linear DE, and that's what we're going to spend time with. And the reason that works for us is, as you saw a few minutes ago, we're adding forces, okay? And that generally fabricates our differential equations. And so by the summation of forces, we fabricate a lot of linear type differential equations. Not completely, but in many cases so. Whereas, say for example, x dot times x plus kx equals 0 is going to be nonlinear. And you'd have, or you could have x dot squared plus kx equals 0, for example, or whatever. This is also. So these become almost specific solutions based on the equation proper. In many cases, they're generally very difficult to solve unless you have a special situation where you can cancel something out or mess around with. We will not be dealing with these very much, if at all. You'll notice in the example I gave with the hydrostatic drag, we are dealing with low velocities. So, you may recall from grade 11, the drag equation has the speed squared, and that is true when you're going fast enough that there's compression. But if you keep the speeds quite slow, if you move your hands through the air just flows around your hand, and then it's a more of a linear arrangement. And so if we make that concession, then we have this linear setup, which is where we have a great amount of theory and way we can solve these problems. Okay, so that is, so we've got the type of differential equation and its linearity. So we're dealing with linear, ordinary differential equations. That's the kind we'll be dealing with. And then we have the order. And this is easier. This is just the level of the highest derivative in the equation. So in this example we have kx dot plus wx equals 0. This is a first order equation because we have a first derivative here. This is dx dt. Remember, the dot implies a derivative with respect to time, distinct from a prime indicator. If we had what we saw a few minutes ago, where we have mx double dot plus bx dot plus kx equals 0, then you have a second order equation. And what we're going to be doing in this particular course, we're going to limit our studies to this situation. Nature is generally not so cruel as to give us too many equations that are beyond this. It doesn't happen, but it isn't too common. But the other thing we're going to do is we're going to have constant coefficients. So in this example, m, b, and k are real numbers, not functions of t. Now this can happen. Certainly happens in nature, but I don't see the need to do that just yet. Now let's consider, this is the equation I established that talked about the motion of a bob connected to a spring going through in a vat of liquid, some kind of damping material. So what do the constants represent? Well, they represent the mass of the bob, which one would hope would be constant. B is the viscosity or hydrostatic properties of the fluid. And if the fluid is non-changing, we'd expect that to be about the same. And the spring, constant K, again, the spring being a mechanical device, we would expect that also to remain very similar. Now, just to give you a moment of terror, to give you an example, we could have a system where the mass is losing lead shot. The water is having an impurity poured into it, could be salt or some other material that changes the water circumstance. And the spring, we could have a torch on the spring or some other way that the spring is changing its properties as we do this. And you can imagine how much more complex the motion would be, because these constants would then be functions of time. Now there is theory to solve those equations and all the rest, but I don't see that we'd be entertaining problems of any kind of that character. So we're going to leave something for the professors, but we can do a great deal just with these constant coefficients, and that's where we're going to limit ourselves. Okay? And just to give you another example where this falls off the wagon when we talk about nonlinear cases, let's just take this one itself. We have a spacecraft that takes off, a rocket takes off from the ground, and we know that it's losing mass because of its propellants coming out the back end. It's also traveling upward, okay, with an increasing speed, and an acceleration that is generated not only by gravity but by the rocket thrust, which is a function of the atmospheric pressure. The aerodynamic drag is certainly going to be a function of the speed squared, but also the density is a function of the altitude. So without even writing it on the board, you can see how these different derivatives themselves depend on the other derivatives in multiplicative or logarithmic manners. And so you're distinctly nonlinear. And what you'll find in many of these cases is that the only way to calculate these things is to do so using a computer. And this is one of the reasons why space flight, or controlled space flight, really never existed until the 1960s, when computers were small enough, or at least controllers were small enough, that a spacecraft could fly, or you could use a computer on the ground to plan the mission very carefully, and then the only objective then was that the rocket do what it was supposed to do. Before that, you would not have adequate control, and you would not be able to predict the flight of the vehicle. And of course, in those days, those calculations were ponderous. Today we can do them in a matter of a few minutes, or seconds even, depending on the nature of them. But you can imagine how difficult it is, and so we end up having to calculate a situation now, move the clock ahead a few fractions of a second, recompute. So we have these very small linear connections together, but we use the mind-numbing number capability of the computer to crunch through these things in real time, and allow us to be able to predict things. One of the most interesting things about simulations like this would be to try and put a spacecraft into orbit, because you realize when they take off, they go straight up. And if you don't do anything, they're going to come straight down. So as the vehicle flies, you have to arc its flight in such a way that when it's finished, its motion is tangential to the surface of the Earth at an appropriate velocity. And so to have to mess around with that and create that to happen is something you can do for entertainment. And it's quite an interesting exercise. And I remember being pretty delighted when I was able to get my first experience of getting a vehicle into orbit where the perigee and apogee were sufficiently high to stay above the atmosphere. So what I wanted to do with all these things, well, these are the basic definitions here. Now I'm going to do one more. I've already talked to you in general terms about the solution, but we need to learn a few more words. And this is where words get used over and over again. As we've talked about in physics in the past, words get used in the common conversation, but have slightly different technical meanings. Sometimes they have wholly different technical meanings. And it's so critical when you are working in this subject, working in your situation, you need to put on your physics hat and remember what these words mean. So, solution of a DE is called a trajectory. Now you might say to me, well, trajectory is a path of an object through space, or through the air, whatever. And that's the everyday language. What you're really saying, and it seems like it's additional language, is it's the ballistic trajectory. Now, ballistic simply means that the motion of an object with only gravity as a factor. So, spacecraft, the Earth's surface is traveling as a function of gravity, and so we can talk about that as a ballistic trajectory. And what we mean is that the path this thing is following, okay, is the solution to whatever kind of differential equation that models this motion based entirely on the forces of gravity. All right, and so, but we've extrapolated trajectory to mean the path of an object, but solutions to differential equations that are dealing with heat flow, dealing with quantum mechanics, magnetic fields, and everything else, they're all called trajectories as well. So this is just a bit of information that you need to remind yourself of as we look ahead. There's types of solutions as well. So when the differential equation is equal to 0, it is said to be homogeneous. And if the differential equation is not equal to 0, this could be a real number, this could be a function, it doesn't matter. This is said to be non-homogeneous. And the theories behind how we solve these solutions depend on whether the differential equation is equal to 0 or not. And we'll come back to that as we work through the specific actual solutions. So you're going to be dealing with these types of situations as we go, and then we need to understand what these words mean. The other thing I wanted to mention is within all of what I've just said, still have some more words. We saw before we had y is equal to x squared plus c. Okay, so if c is left as a variable, or as, let's say, left unevaluated, then we have what is called the general solution to this differential equation. And if it's evaluated, then we say it's the particular solution. Now, how would we evaluate C? So C, in this example, is found by substituting initial conditions. And we call those ICs. There's lots of acronyms with differential equations, which are also given with the question. An example might be y of x equals 3. And so you go and say, okay, well, if I have x equal to sorry, pardon me, y of 2 equals 3. So I'm going to have 2 squared, right? And this is equal to 3, therefore that's -1. And that forces it. So you have one condition like this for a first order equation. And for second order, we need 2 conditions. Because typically, we're going to be integrating twice in one way or some way or other to solve a second order equation. So we would have something like this where we'd say, okay, so first order, we have one initial condition. Second order equation, we would have to have 2 initial conditions. Both of these, of course, would then lead to the particular solution. So it will depend on the context as into whether you're computing a particular solution or something like the general solution. And general solutions have use as well, so I don't want to be too fussy about this. Okay, so we have these different aspects of naming not only the equations themselves and their types, but also aspects of the solutions as well. So these are fairly common. Another point that's a bit different with differential equations is phase plots. And this is something that I'm going to let you play with a bit yourself. But generally speaking, what we have here is something like this. We have y of x here and y prime of x here. And you'll often get situations where it's circular or oval or all kinds of strange things can happen. And these are known as phase plots. So one derivative plotted versus another. So plotted with respect to the function or other derivative. And these can be instructive for the scientist looking at whatever it is we're trying to do here, okay? So you can take oscillatory motion, for example, a pendulum going back and forth. If you plot its acceleration and so on, you basically have a sign on the coast and you're going to get a circle. So things like that happen, okay? So those are some of the basic terminologies that we have. And I've also talked about separating variables already. I'm not going to beat that up too much in this course. I want to get to things that are more relevant to what we're going to be solving things. So that was that's my introduction, and then the next little lesson we'll have here will be dealing with first order differential equations.